Alright, so in this video we will cover how to solve some basic sequence problems. So we will begin with more simple problems, and then as we move along we will move to more complicated problems. So here's the first problem. It states, calculate the first four terms of the following sequence starting with n equals 1. So I'm going to begin by just simply rewriting the equation really quickly. So the equation is 9 multiplied by 3 to the power of n divided by n factorial. And all we have to do from here is plug in the number that they want us to plug in. So for this case, it will be 1, and then 2, and 3, and then 4. So if we begin with 1, we're going to have c sub 1 equaling 9 times 3 to the power of 1 divided by 1 factorial. This will end up being just 9 times 3 on top, and then divided by n factorial, when n is 1, it's simply going to be just 1. So then the answer for this one is 27. And now for c sub 2, we are going to have 9 times 3 to the power of 2 divided by 2 factorial. And then on top we're going to have 9 times 3 squared, which is 9. And then it's going to be divided by 2 factorial. And 2 factorial is simply 2 times 1. And 9 times 9 is 81. And then it's going to be divided by 2. And you can leave the answer as a fraction like this, or just write down 40.5. But I'm just going to leave it as a fraction. So 81 over 2. And now for c sub 3, we're going to have 9 times 3 to the power of 3 divided by 3 factorial. So on the top we're going to have 9 multiplied by 3 cubed. 3 times 3 is 9, and 9 multiplied by 3 again is 27. And then it's going to be divided by 3 factorial. So 3 times 2 times 1. So the top will be 243, and then the bottom will be 3 times 2, which is 6. And then this will also simplify to 81 over 2. So we're going to have 81 over 2 as an answer for this one as well. And then finally we're going to have c sub 4, which is going to be 9 times 3 to the power 4 divided by 4 factorial. This will equal to 729 divided by 4 times 3 times 2 times 1. So on top we're going to have 729, and it's going to be divided by 4 times 3 is 12 times 2 is 24. And then once you simplify this, it'll come out to 243 over 8. So that's the answer for the last one. Alright, and here is our next problem. It is pretty much identical to the last one that we just did. And once again, I will begin by just simply rewriting the equation. So we have c sub n equals 2 plus 2 over 2 plus 2 over 3, and then plus dot 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 plus 2 over n. And when you first look at this equation, you might be a little bit confused about what exactly is going on or what you're supposed to do. But really, all it's asking is to add 2 over n every single time. So for example, at c sub 1, we are going to have 2 over n. And n is 1 at the moment. So this will be 2 over 1, which is simply 2. So the answer is 2. And then when we move on to c sub 2, we are going to have the 2 that we had previously plus an additional 2 over n. And in this case, we know that n is 2. So it's going to be 2 plus 2 over 2, which is 2 plus 1, and it's just 3. And the pattern will continue from here. So for c sub 3, we're going to have the previous answer, which was 3, and we are going to add 2 over n, which is again 3. So 2 over 3. And the answer for that one will be 11 over 3. And then for the last one, c sub 4, we are going to have the previous answer, 11 over 3, and we are going to add 2 over n, and n is 4, so 2 over 4. And the answer for that one will be 25 over 6. And for this next question, it is going to be a little similar to the last few that we did, but a little different as well. So notice how they gave us some terms right away. like b sub 1 and b sub 2, but they also gave us a recurrence formula. And with the help of our recurrence formula, we can define any term that we want as long as we have the previous terms. This differs from an explicit formula, which is what we were dealing with the last two problems. In the last two problems, we were able to plug in any number n and get the term that we wanted at any given point. But with this one, we need more information than just plugging in a number. So notice how in this equation we have b sub n equals 5b n minus 1 and then 4b n minus 2. So for example, if we were to plug in a 3 in here, we would need to know what b sub 3 minus 1, which is 2, is, and also b sub 1 if you do 3 minus 2. And if you don't have those terms, then you will not be able to find what you're looking for. And again, this is different from an explicit formula. With an explicit, you could plug in any n and you could get the answer. So let's begin with what they gave us. So right off the gate, we know that b sub 1 is 9. So we can just put 9 in there. And with b sub 2, it's going to be 5. So b sub 2 is 5. Now let's pay attention to the recurrence formula. So we have b sub n equals 5b n minus 1 plus 4b n minus 2. So let's begin by solving for b sub 3. So b sub 3 will equal 5 multiplied by b n minus 1. At the moment n is 3, so we're going to have 3 minus 1 at the bottom, and then plus 4 b and then n minus 2, so 3 minus 2. So this ends up looking like this. So b sub 3 will equal 5 b sub 2 and then plus 4 b sub 1. So notice how b sub 2 and b sub 1 are terms that we do currently have. B sub 1 is 9 and b sub 2 is 5. So all we have to do now is just replace them and substitute them for the terms here. So b sub 3 will equal 5 multiplied by b sub 2, which is 5, plus 4 multiplied by b sub 1, which is 9. So then b sub 3 will equal 61. And then for b sub 4, we will do the exact same thing. So b sub 4 will equal 5 b n minus 1, n is 4, so we're going to have 4 minus 1, and then plus 4 b 4 minus 2. So b sub 4 will equal 5 multiplied by b sub 3 plus 4 multiplied by b sub 2. And once again, notice how we do currently have b sub 3 and b sub 2. B sub 3 is 61 and b sub 2 is 5. So all we have to do again is replace the numbers with the terms. So b sub 4 will equal 5 multiplied by b sub 3, which is 61, plus 4 multiplied by b sub 2, which is 5. So b sub 4 will end up being 325. And those are your answers for this question. Alright, and so for this next problem, you will notice that it's completely different from the rest. So now we have to work with the given terms to create a formula. Alright, so let's begin with A. So for A, we are given 1 over 1 as the first term, and then negative 1 over 4, and then 1 over 9. And for these types of problems, I would highly recommend writing down what term is what. So for example, this first one is the first term, so when n equals 1. For this one, it's n equals 2, and then n equals 3. So now let's begin by finding patterns. And generally speaking, the only way to solve these types of problems is by finding patterns. So I would highly recommend for you to practice more problems like this over and over again and find different patterns and different problems, because at the end of the day, the only way that you're going to be able to solve these is by practicing them. And the first thing that I would notice is that every term here is fluctuating from positive to negative. So the first term here is positive, the next one is negative, and the next one is positive again. So what is a way that we can create such a fluctuating action here? So let me just quickly write down the first pattern that we saw. So we know that it's alternating. So we know that it's going from positive to negative to positive. So what can we do with that? So one way that we can get that fluctuating plus and minus is by having -1 to the power of n. So now you can see that if we plug in an odd number, like 1 or 3, then we will get a negative answer. We're going to have a -1, which is exactly what we have in the second term. If we plug in an even number, like 2, -1 times -1 is +1, so we're going to get a positive. But then you notice that for our first term here, when n equals 1, we are actually going to get a negative answer. So we need to shift it. So if we have n plus 1, for example, we are now starting at 1, and we would have n equaling 1, so 1 plus 1, which would be 2. And we know that -1 times -1 is +1. And that's how we get a positive. So we're going to have to shift it +1. And now let's confirm that our answer works by testing the second term, n equals 2. So if we have -1, and then to the power of n, which is 2 plus 1, this will equal -1 to the power of 3. -1 times -1 is +1, but then times -1 makes a negative. And we have a negative, which is what we have right there. So we know that it works. So our first pattern there is complete. So now let me just go ahead and get rid of these since we do not need them any longer. And now let's talk about the numerator. So just the top. So let me write down numerator here. And what do we see? Well, we see that it's 1 every single time. And n equals 1, it's 1. N equals 2, it's 1. And for 3, it's also 1. So it's going to stay 1 forever. What does that tell us? And don't overcomplicate the answer to that question, because the numerator will stay 1, meaning that when we have our final equation, our final formula, the top numerator will be just 1. That's all it means, so don't worry about that too much, since it stays 1 consistently. If that were a 2 instead, we would write a 2. But we can't do much besides that. It stays at 1 and it's going to stay at 1 forever. And now let's talk about the denominator. So let me write down denominator. So what do we see? So the first denominator is 1. And then when n equals 2, the denominator is 4. And for 3, it is 9. So what kind of pattern can we see between these 3 terms here? So I would suggest by just trying random things out. And what I mean by that is just try to find patterns. So from 1 to 4, it's adding by 3. So maybe it's adding by 3 every single time. But then we go to 4 to 9, and it's adding 5, not 3. So it's not adding. How about multiplying? Well, if we multiply 1 by 4, we get 4. But if we multiply this 4 by 4, we do not get 16, we get 9. So it's not multiplying by a common ratio either. Now, here is why writing down the term right below the term is really important. So if you look at the nth term as well as the denominator, you will eventually probably see a pattern. So if we square 1, 1 times 1 is 1. How about if we square 2? 2 times 2 is 4. And how about if we square 3? Well, 3 times 3 is also 9. So now you see that we're actually squaring whatever n is. So for our denominator, we can write down n to the power of 2. So then every single time with the denominator, we're going to have whatever n is. If it's 100, it's going to be 100, and then square it. And then that's what the denominator will be for the 100th term. And that might not be as easy to see if you didn't have the n equals 1, n equals 2, and it might take a little bit more work to see that. So I would always recommend to just write down what term you're on for every term that you're given. So now let's put it all together. So let me just create a brace over here, and our answer will be over here. So on the numerator, we are going to have -1 for starters, and then n plus 1. That will create the fluctuating positive and negative signs. And then also on the numerator, we're going to need the 1 right here. And this is going to be multiplied by 1. That 1 is insignificant as it's just 1. And then on the bottom, the denominator, we are going to have n squared. And that's it. That is the formula for this specific sequence. Now if we want to simplify it a bit more, again, we don't need the 1, so we could just write down negative 1 to the power of n plus 1 divided by n squared. And we can test it if we want to. So let's use our equation to find n equals 3. We know that it should equal positive 1 over 9, so let's check. So we're going to start with negative 1 multiplied by n, and n is 3 at the moment, and then plus 1 divided by n, which is 3, and then square it. So then on the top, we're going to have negative 1 to the power of 4 divided by 3 squared, which is 9. Now whenever we have a negative number to the power of an even number, we are going to have a positive outcome. So the answer will be 1 over 9. And as you can see, the 1 over 9 does indeed match what we have for the third term. So our formula here is correct. So that's your answer for A. So we're going to have negative 1 to the power of n plus 1, all divided by n squared. And then let's move on to the next one. So let me go ahead and delete all these things here since we do not need them any longer. So how about this next one? So the next sequence has these terms. We are given 3 over 6, 4 over 7, and 5 over 8. And once again, I'm going to begin by writing down the n term. So we have n equals 1 here, and then n equals 2, and n equals 3. That looks like an m. Sorry about that. Here we go. N equals 3. So here are the 3 terms that we were given. So once again, let's look for some patterns. So is it alternating like the last one? And if we look, the answer is no. This one's positive, and this one's positive. So we can't really use that as a pattern. But we're still going to have to figure out what kind of pattern is happening in the numerator. So let me begin by writing down numerator. And then what are the terms in the numerator? So we have not 1, but 3. We have 4 and 5. So what is happening? What's the pattern between those numbers there? And you might eventually notice that every time we move an n up, we are going to add 1 to the numerator. But the problem now lies with the 3. We have to correlate n equals 1 to 3. Because we're not starting at 1 and then adding 1 every single time. We're starting at 3. So how do we fix that? So it's going to be kind of similar to the alternating problem that we had in the last one. So in the last problem, we had negative 1 to the power of n, but we had an issue with the n, so we had to shift it plus 1. So what we're going to do here is pretty much the same thing, but with the numerator. So let's begin by writing down n. So we know that we're looking at this term when n equals 1. So at the moment, we should think of this n as 1. So what do we need to add to get to 3? So we have 1, and if we add plus 2, we are going to end up with 3. And now let's test it. So now let's try the third term. So the numerator should be n equals 3, so we could substitute the n for 3. 3 plus 2 is 5. And the numerator on the third term is indeed 5. So we have the numerator pattern down. Next, let's look for a pattern in the denominator. So let me write down denominator. And what do we see? So we have a 6, a 7, and an 8. So what is happening here? And once again, it's kind of similar to the situation in the numerator. We see that every time we move up, we are moving plus 1. But again, we have an issue with the 6. So when n is 1, the denominator is 6. So we need to correlate those two together. So once again, like the numerator, let's just start with n. So what do we need to do to n to get to 6 when n is 1? So again, let's think of this n as a 1. So we're going to have 1, and then if we add 5 to that, we're going to have 1 plus 5, which is 6, which will get us that 6 in the denominator. So now let's test that theory with the third term again. So if we want to find the denominator for the third term, let's substitute the 3 for the n. So we're going to have 3 plus 5, which is 8. And the denominator on the third term is indeed 8. So we have confirmed that this is valid. And now let's put it all together. So in the numerator, we're going to have n plus 2. And then on the bottom denominator, we're going to have n plus 5. And like the last one, we could just go ahead and test it just to make sure. So let's go ahead and try to find the second term if we didn't know it already. It should be 4 over 7, positive. So we're going to have n equals 2. So when n equals 2, we're going to have 2 plus 2 divided by 2 plus 5. And this will be 2 plus 2 is 4 divided by 2 plus 5, which is 7. And we do indeed come back to the 4 over 7 that we had over here originally. So this equation is the answer. So n plus 2 divided by n plus 5. So what we have found here are two explicit formulas. These explicit formulas can help us find the term on these sequences that we found. So for A, this equation for A will give us the term of the sequence at any given point that we want. We could find the 100th or 1000th term. It doesn't matter. We don't even need to have any prior terms in the sequence to find the answer. We could just plug in an n and we'll find it. And that goes the same for B. And really the key to finding these formulas is to just do them over and over again and get more practice with different patterns that you might find, because they're going to be random quite a lot of the time. Sometimes the denominators will be multiplied by a common ratio, sometimes they'll be cubed, or maybe to the power of 4, but it'll change every single time. Alright, so now we're going to move on to the idea of convergence and divergence. And it is important to note that there are many ways of testing convergence or divergence for a sequence, but typically solving for the limit of a sequence, such as the sequence right here, will be enough to determine whether it will converge or diverge. It will all depend on what the limit is. So very quickly, let's go over some basic sequence information. So first of all, what exactly is a sequence? Well, a sequence, like the sequence that we have here of a sub n, will simply equal a list of terms. And now how does this list of terms correlate to the idea of convergence and divergence? So in the most basic of terms, a list of terms will converge if the list of terms will approach a real number L as we move to infinity. So let me just write that down. So it's going to converge if the limit of the sequence a sub n as n approaches infinity will equal L. And L can be any number. It can be 1,000, 1,000,000, it doesn't really matter. But the point is that it has to equal a real number L. So what about divergence? So a sequence will diverge if the list of terms goes to infinity, negative infinity, or if it simply does not exist as we move to infinity. So let me just write that down so we have that written down as well. So it will diverge if the limit of the sequence a sub n as n approaches infinity equals positive or negative infinity, or it doesn't exist. So testing for convergence and divergence of a sequence is not that hard. All you have to do is keep this basic idea in your head. So if a limit of a sequence approaches a real number, it could be any number, it will converge to that number. But if the limit of that sequence ends up being positive or negative infinity, or if it doesn't exist, then it's going to diverge. So let's begin with this first problem here. We will begin with very simple formulas for sequences and then add more complex ones later on. So let me just delete these things. So here we have the sequence a sub n, which simply equals 5. So if we were to graph this on a graph, we would have 1, 2, 3, 4, 5, and then the 5 will simply be flat. And then you can have your x coordinate plane here, and then your y over here. And then, or in this case, we're not talking x, we're really kind of talking n. So as n approaches infinity, meaning that as we move along this axis here to to infinity, you'll notice that this line here, the graph of 5, will always remain 5. So this will never ever change. So the idea is that no matter how much you move to the right over here towards infinity, positive infinity, or even negative infinity, the graph will never change. It'll stay at 5 the whole time. So now let's formally write it as a limit. So we're going to begin by writing down the limit as n approaches infinity, meaning as we move to infinity on this graph, as we keep moving over here to the right, of the sequence a sub n, and then let's substitute a sub n for 5. So we're going to have the limit as n approaches infinity of the formula 5, or graph 5, will equal 5, since it's always going to equal 5. So since it equals a real number L, as we just talked about earlier, this will converge to 5. So we can write down that it's going to converge to 5. And that's it for this problem. So now we have this problem. So once again, let's begin by taking the limit of it. So we're going to have the limit as n approaches infinity of the sequence a sub n. It's going to equal the limit as n approaches infinity of 20 minus 12 over n quartic. So from here we have to pay attention to this 12 over n quartic. So let's say n equals 1. If we take the 12 over n quartic, it's going to be 12 over 1, which is just 12. Now let's say n is 100. What will happen then? So we're going to have 12 over 100, which, if you have trouble conceptualizing what that is, it is 0.12. What if n equals 1,000? We're going to have 12 over 1,000. So what does that equal now? That's going to equal 0.012. What if n equals 1,000,000? We're going to have 12 over 1,000,000. What does that equal then? That's going to equal 1.2 times 10 to the power of negative 5. In other words, it is a really small number, really close to 0. So what exactly is happening as we move along higher n values? So you start to notice that the higher we go in n's, we get closer and closer to 0. Now we will never reach 0, but we're going to get really close to it. So as n moves to infinity, as we have on our limit here, this will actually just end up being 0. It's really insignificant when we consider the whole limit. So we can just simply write limit as n approaches infinity of 20. Because again, this is really insignificant as we start getting to the bigger n values. As you can see, when n equals 1,000,000, it's really close to 0. It's pretty much 0 to the point that this doesn't even matter. So the only thing that does matter and ends up making a huge difference about the graph is this 20. So kind of like the last problem where we had the limit as n approaches infinity for 5, we have a single constant here. So it's going to remain at 20 for the most part. So we can say that this sequence here, a sub n, will be converging to 20. So converges to 20. And that's your answer for this problem. So what about this problem? So this problem is not as simple as the last two, where we can just consider one of the graphs or equations to be 0. So as you can see, this formula is a little bit more complex. So let me begin by rewriting a sub n, just so we can see it a little bit more clear. So a sub n here is 2n over the square root of 4n squared plus 4. So now we need to take the limit of this equation here to find whether it's going to converge or diverge. So let's begin by writing the limit of a sub n as n approaches infinity, and then rewrite it as the limit as n approaches infinity of the function 2n over the square root of 4n squared plus 4. So what do you think we should do from here? So whenever we have a fraction where we have different n terms with different degrees, we always have to multiply both sides, the numerator and the denominator, by 1 over and then the greatest n term in terms of degree. So when you look at this equation, which n term has the highest degree? And you notice that it's this one, it's n squared. This one is only n to the power of 1. So we're going to have to multiply everything by 1 over n squared. But unfortunately, it is not as simple as multiplying both sides by what we have right here. And that is because of the square root. So to overcome that, we're going to have to multiply both sides by the square root of 1 over n squared. So when we do this, we can multiply both of the arguments within the square roots. So when we multiply the bottom by the square root of 1 over n squared, we can multiply the 1 over n squared by the argument inside of this square root. And to multiply the numerator, I'm going to rewrite this a little bit differently. So this will also equal the square root of 1 over the square root of n squared. So then this will equal 1 over n, as the square root and the square here will cancel. So we're going to multiply the top by 1 over n. These really are the same thing. As you can see, this equals this when we calculate it out. But there will be times where it looks different like this. For other problems, it'll be the exact same thing that we're multiplying it by. Again, it is the exact same thing, but it looks different. But other times it won't be like this. It's just the square root in this problem creates a little bit of an issue. So now when we multiply this out, we're going to have the limit as n approaches infinity. And then the top, the n's will cancel. So we're going to have a 2 on the numerator. And then on the denominator, we're still going to have the square root. And then we're going to have 4n squared multiplied by 1 over n squared. So the n squares are going to cancel. So we're going to be left with just a 4 here. And then plus, we're going to have 4 multiplied by the 1 over n squared. So we can put the 4 on top and then over n squared. And then notice how this part here is similar to the first problem that we encountered. So we already know that as n gets bigger and bigger, this term here that's circled, 4 over n squared, will be getting closer and closer to 0. So it's insignificant. So we can now rewrite this as the limit as n approaches infinity of 2 over the square root of 4 plus 0. Because again, this will be approaching 0 as n gets really big. So it's insignificant at this point. We can drop it. So then from here, we're going to have 2 over the square root of 4, which is simply 2 over 2, which is just 1. So now we can say that the limit as n approaches infinity of our sequence a sub n is going to equal 1. This means that this sequence will be converging to 1. And there's your answer for this problem. So what about this problem? So let me rewrite it really fast. So here we have a sub n equaling 7n squared plus n plus 2 divided by 5n squared minus 3. So let's begin by writing the limit. So we're going to have the limit as n approaches infinity of a sub n is going to equal the limit as n approaches infinity of this function here. 7n squared plus n plus 2 divided by 5n squared minus 3. So from this point, there are two ways to solve this. There's a quick method and then the regular method. So I'm going to cover the quick method first. So in the previous problems, we multiplied both sides of the fraction, that being the numerator and the denominator, by the highest degree variable. So in the previous problems, we multiplied problems like these, where we have a fraction, by 1 over, and then the variable with the highest degree here, so whatever this was. So let's say that we had a fraction where we have n and then n squared, so we would multiply both sides by 1 over and then n squared, because n squared is the variable with the highest degree. So we would multiply both sides by 1 over n squared. And the purpose of this is that we would have on the top n over n squared, so we would end up having 1 over n divided by 1, which is just 1 over n, and we could end up canceling this out as a 0, because as n approaches infinity, this will become a 0. So that's why we did all this. But what happens when we have a fraction like this, in which the variable with the highest degree is equal on both the top and the bottom, the numerator and the denominator? So here's where the trick comes along. If the variable with the highest degree is equal on both the numerator and the denominator, all we have to do is look at the leading coefficient of that variable. So in this case, the leading coefficient for the n squared at the top is 7, and on the bottom it's a 5. And that's all you have to look at. In this case, the answer is 7 over 5. So we can say that this sequence here, a sub n, is going to be converging to 7 over 5. Now let's talk about why this works. And to do that, we're going to solve it the regular way first. So let me go ahead and delete this and redo this. So we're going to have the limit of 7n squared plus n plus 2 divided by 5n squared minus 3. So as we talked about previously, the variable with the highest degree here is n squared. So they're both even, so we're just going to multiply both sides of this fraction by 1 over n squared. So this will end up being the limit as n approaches infinity, and then this term here will cancel out to just a 7, and then we're going to have plus, and then n over n squared, the n on top will cancel, and we're going to have 1 over n, and then we're going to have 2 over n squared. And then on the bottom, we're going to have the n squares cancel, so we're going to have a simple 5 minus 3 over n squared. So notice how these three fractions here have the variable with the highest degree on the bottom. And as we've seen many times, whenever this happens, we can just mark them as zeros because they become insignificant as n becomes really big. So then this would end up turning into 7 plus 0 divided by 5 minus 0, which again is just 7 over 5, which we get to the same answer if we do it the long way. So notice how the variable with the highest degree is the only one that ends up meaning anything. So whenever we have matching highest degree variables on the numerator and the denominator, the rest and the following terms will not really mean anything. So this n will cancel, this 2 will cancel, and this 3 will cancel. The only ones that really matter are these when they're equal. So that's what we could end up just saying 7 over 5. Just look at the leading coefficients of those variables. But if you forget that little trick, then you can always just fall back to solving it the normal way. Just multiply both sides of the equation by 1 over, and then whatever the variable with the highest degree is on the bottom, on the denominator. And if you follow that, you will get the same answer at the end. But once again, we can say that this sequence here will be converging to 7 over 5. And that's the answer for this question. So now take a look at this problem. So now we're dealing with a natural log. So let me begin by rewriting this. So we have the sequence c sub n equals the natural log of 2n minus 7 divided by 11n plus 4. So how do we deal with a natural log when we're talking about limits? So here we have the limit as n approaches infinity of c sub n, which is the limit as n approaches infinity of the natural log of 2n minus 7 divided by 11n plus 4. So something you can do is just take the natural log of this limit. So what I mean by that is just write natural log and then put the limit inside of the natural log. So we're going to have the limit as n approaches infinity of 2n minus 7 divided by 11n plus 4. So now just solve for what's inside of the parentheses, inside of the natural log, and that'll be your answer. And now notice how the variable with the highest degree is the same on the numerator and the denominator. So up here, there's a degree of 1, and the same goes for the denominator. So we can use the trick that we used last time to make this a little bit more simple. So this is going to equal the natural log of the limit as n approaches infinity of 2 over 11, since we only care about the leading coefficients now. So this ends up equaling the natural log of 2 over 11, since this is going to be a constant graph that never changes as we move n to infinity. So there's your answer. This sequence here, c sub n, will be converging to the natural log of 2 over 11. And that's how you solve this problem. So what happens when we're dealing with a factorial? So here we have a sub n equaling n plus 1 factorial divided by n plus 2 factorial. So we're going to start off with the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of n plus 1 factorial divided by n plus 2 factorial. So I would recommend starting off by trying to simplify this. So which one of the two, n plus 1 factorial or n plus 2 factorial, which one is bigger between those? It turns out that n plus 2 factorial is bigger than n plus 1. So we should begin by trying to split apart n plus 2 a little bit until we can match n plus 1 and cancel out terms. So on the top we're going to leave n plus 1 factorial alone, and that'll be divided by, we're going to have n plus 2 and then multiplied by n minus 1, so it's going to be plus 1, and then factorial. And now notice how we can cancel out the n plus 1 factorials, and we're going to be left with just 1 on top divided by n plus 2. So now our limit can simply be the limit as n approaches infinity of 1 over n plus 2. And now let's multiply both sides of the fraction by 1 over n, since the highest degree variable here is n to the power of 1. So this will turn into the limit as n approaches infinity. On the top we're going to have 1 over n, and then on the bottom the n's will cancel for the first term, so we're going to have 1 plus 2 over n. So then we're going to have the limit as n approaches infinity. This will turn into a 0, and then we're going to have a 1, and this will also turn into a 0. So now the final answer is 0 over 1. So the answer is just 0. So even though the answer is 0, it is still converging to a real number, as 0 is a real number. So this sequence here will be converging to 0. And then there's your answer for this problem. So what about something ugly that looks like this? So here we have a sub n equals n multiplied by sine of 1 over n. So we would start off by having the limit as n approaches infinity of a sub n, and this will equal the limit as n approaches infinity of n times sine of 1 over n. So at this point you're probably stuck wondering what you should do. The first thing you should do is rewrite n. So we can easily rewrite n as 1 over 1 over n. And when you end up undoing what we just did, you will get n on its own again. You could just multiply both sides by n, and then you're going to get 1 in the denominator, and then an n on the top, which is just n. And you'll see why I did it this way in a bit. So now we have the limit as n approaches infinity of 1 over n multiplied by sine of 1 over n. So let me rewrite this one more time. Not really rewriting, but kind of rearranging things. So we're going to have the limit as n approaches infinity. Let's put sine on the top. So we're going to have sine 1 over n, and then times the 1, but we don't have to really do that. And then this is going to be divided by 1 over n. So from this point, we unfortunately cannot make this 1 over n turn into a 0, because if we put a 0 down here, we are going to break this function, and we will not be able to work with that, unfortunately. So what we have to use from here is L'Hopital's rule. So we're going to have to take the derivative of the top and the bottom until we can get a number that we want. So let's rewrite 1 over n as n to the negative 1 to make the derivative So let me quickly rewrite 1 over n as n to the negative 1. This way taking the derivative of this becomes a little bit more clear. So this will turn into n to the power of n minus 1, which is negative 2. And then it'll also be multiplied by negative 1. So this will be negative n to the negative 2 or negative 1 over n squared. So that's the derivative for the denominator. What about the numerator? So let me do this on the top left. So the derivative of sine will be cosine, and then we're going to leave what's in the parentheses as it is right now, so 1 over n. And then according to the chain rule, we have to multiply by what's inside of that cosine now, by the derivative of that. And we know that the derivative of 1 over n, as we just calculated, is going to be negative 1 over n squared. So now we're going to have the limit, as n approaches infinity, of cosine 1 over n multiplied by negative 1 over n squared divided by negative 1 over n squared. So from here we can simply cancel out these two, and we're going to be left with the limit as n approaches infinity of only cosine 1 over n. And now take a look at the parentheses here. So we have 1 over n. So as n gets really large, this will actually just turn into a 0. So we're going to have the limit as n approaches infinity of cosine of 0. And cosine of 0 will simply be 1. So this sequence will be converging to 1. And that's the answer to this problem. And now what do you think we should do for a problem that looks like this? So we have a sub n equals sine of n divided by n. So for a problem like this, we're going to have to use something called the squeeze theorem. So let's begin with three functions. We have f of x, and then we have g of x, and h of x. And then let's say that g of x will be greater than or equal to f of x, and h of x will be greater than or equal to g of x. So according to the squeeze theorem, the limit as x approaches a constant c of f of x equals L, and that the limit as x approaches c of the function h of x also equals L, then the limit as x approaches c for the function g of x will also have to equal L. So if the limit of the function f of x and the limit of the function h of x equal the same number L, then the limit of the function g of x will also have to be the same. To make this a little bit more clear, you can think of L as an actual number. So let's say that instead of L, we had, let's say, the number 4 or something like that. So now let's replace 4 with the functions here. So instead of f of x equaling L, let's make it 4. And then we're going to have the less than or equal symbol here, and then g of x will be in the middle, and then we're going to have this symbol here, and then h of x will also be 4 as we just wrote it down here. So when you look at it like this, it makes a little bit more sense. So the only options for g of x to be are 4, because let's say if this is something like 5, 5 will be greater than or equal to the 4 on the left, but then it's not going to be less than or equal to 4. If it's lower, like 3, let's say, it will be less than or equal to 4 on the right side, but it will not be greater than or equal to than the 4 on the left side. So the only possibility now is for g of x to also equal 4. That's pretty much what's happening here. If the limit of f of x is approaching a number L, and the limit of h of x is also approaching that same number L, then the only option left for g of x to be is for it to be approaching L as x approaches the same constant c. So let's go ahead and apply that to this problem here. So if we were to graph sine of x really quickly, that's a pretty bad graph, but it would look something like this. What's important to note here is that it's going to be fluctuating between positive 1 and also negative 1 right here. And it'll never go below negative 1, and it'll never go above positive 1. So we can say that sine of x, or sine of n in this case, will always be in between that negative 1 and the positive 1. So it's going to be greater than or equal to the negative 1, and it's also going to be less than or equal to than the positive 1. It's bounded. So now let's divide everything by n, since our sequence is dividing sine by n. So if we divide this by n, this by n, and this by n, we can use the squeeze theorem. So taking the limit of the middle is the same thing that we had in the beginning. We can't do it yet. So let's take the limit of the boundaries. So let's do this one first. The limit as n approaches infinity for -1/n will simply equal 0. Because as n gets bigger and bigger and bigger, we're going to have -1 over 100 or over 1,000. It doesn't really matter. It's going to be getting closer and closer to 0. Now let's talk about the other boundary. So for this one, we're going to have the limit as n approaches infinity for 1/n. And again, same thing. As n increases, this will just be approaching 0. So now since the limit of -1/n is 0 as n approaches infinity, and the limit as n approaches infinity for 1/n is also 0, then according to the squeeze theorem, the limit as n approaches infinity for the function sine of n over n will have to be and can only be 0. So we can say that the limit as n approaches infinity for our sequence a sub n, which is sine of n over n, will be converging to 0. And that is how you solve something like this. Now for this last problem, we will be tackling something pretty hideous. So here we have a sub n equaling 1 plus 1/n to the power of n. So let's begin by writing the limit down. So we're going to have the limit as n approaches infinity of the function 1 plus 1/n to the power of n. So this problem is completely different from any other ones that we have done before. For this one, we're actually going to require to set this limit equal to y. And after that, we're going to have to take the natural log of both of these sides as well. So let me begin by moving this natural log inside of the limit to make this next step a little bit more clear. So we're going to have the limit as n approaches infinity of the natural log of 1 plus 1/n to the power of n. And this will equal the natural log of y. So a property of a natural log allows us to move the exponent to the front. So then we're going to have the limit as n approaches infinity of n multiplied by the natural log of 1 plus 1/n. And then this will equal the natural log of y. And then, like we did a few problems ago, I'm going to rewrite n as 1/1/n. So now let's write the limit down here. So we're going to have the limit as n approaches infinity of 1/1/n multiplied by the natural log of 1 plus 1/n, and then it's going to equal natural log of y. And if we rewrite this one more time, we're going to have the limit as n approaches infinity of, let's write the natural log on top, so we're going to have the natural log of 1 plus 1/n divided by 1/n, and then this is going to be equal to the natural log of y. And then once again, like one of the last problems that we did, if we make this 1/n a 0, because as n gets bigger, we said that we can just change these to 0 because as n gets bigger, we're going to just approach 0 anyway. But we approach it the same problem that we had last time. We cannot simply put a 0 down here because we're going to break the function, and we don't want to do that. So like before, we're going to have to use L'Hopital's rule and take the derivative of both of these sides of the fraction. And then we'll try again and see what happens. So let me clear some space up here and work on the derivatives. So we have the natural log of 1 plus, and let me rewrite this 1/n as n to the power of -1. So u will be 1 plus n to the -1. And u prime will be, the 0 will go away, and then we're going to have -1 multiplied by n to the power of -2, n minus 1. This also equals -1 over n squared. And the derivative of any natural log function will be equal to u prime over u. So u prime is -1 over n squared, and then u will be the original argument, which was 1 plus 1/n. I just rewrote it once again to what it was originally. And then the derivative of the denominator 1 over n. So 1 over n, let's rewrite it as n to the negative 1. This will be negative 1 multiplied by n to the power of negative 2, which is once again negative 1 over n squared. So let's begin with the problem up here on the top left. So now we're going to have the limit as n approaches infinity of, we're going to have the numerator's derivative, which is negative 1 over n squared divided by 1 plus 1 over n, and this will all be divided by the denominator's derivative, which is negative 1 divided by n squared, and then this will all be equal to natural log of y. So this is a big mess right now. So to not confuse anyone, let me just go ahead and get rid of everything we no longer need. So all of this can go away. We're only focused on this part now. And one of my main concerns is the denominator here. I want to make this a little bit more simple and not have fractions within fractions. So let me go ahead and multiply both sides of this equation by negative n squared. And by doing so, we're going to cancel the negative sign as well as the n squared on the denominator here. And then on the numerator of the numerator, we're going to cancel out the negatives as well as the n squared. So now this equation will look a lot cleaner. So we're going to have the limit as n approaches infinity. And then we no longer have this over here. So now we're just going to have a 1 over, and then the bottom here, the denominator of the numerator, 1 plus 1 over n. And then the bottom of this one is simply 1 now because we canceled everything out. And then this will equal the natural log of y. Don't forget that. And then once we clean this up, it's going to be the limit as n approaches infinity of 1 over 1 plus 1 over n, and then this is going to equal the natural log of y. And from here now, it is perfectly okay for us to substitute this 1 over n as a 0, because we're not going to be breaking the function because of this 1. So now we're going to have the limit as n approaches infinity of 1 over 1 plus 0, and then it'll equal the natural log of y. And then once we get rid of the limit here because we don't need it anymore, we're going to have 1 over 1 equaling the natural log of y, which is simply 1 equals the natural log of y. And now the goal is to solve for y. So the natural log has a base of e. And then if we convert this to exponential form, the base will be e, as we just said, and then the exponent of this base will be 1, and this will all be equal to y. So then y will equal e to the power of 1, which is just e. So now let's just rewrite the original equation, which was the limit as n approaches infinity of the function 1 plus 1 over n to the power of n. So now we know that this simply equals e. So we know that this sequence will be converging to e, which is a number. So that is how you solve this atrocity of a problem. And this will be the end of this video. So thank you for watching, and I hope that you learned something new. And by the way, I want to give credit to the organic chemistry tutor. I took some of his problems that he used in his video for my video here because I just wanted to practice them, and I think they were really good examples. So props to the organic chemistry tutor. But yeah, I gotta give the credit to him for those problems, the last few. But yeah, thank you so much for watching.